Hello, everyone. Today we're going to be talking about types of chemical reactions. We're going to be talking about the three broad categories, and then we're going to be talking about the subcategories within those, or the different types that can fall into the three main categories. So hopefully it will be clear when we start looking at it, the different main types, but then they can also be called smaller types as well. So we're going to be addressing that. Part of it will be PowerPoint slides, and then part of it will be some illustrations that I'll be doing on the board behind me. So bear with me as we flip back and forth so that you can have the visuals that you need for the understanding in this course, or this part of the course. So the three main categories that we look at are called acid-base reactions, also known as neutralization. We have oxidation redox, or redox for short. So oxidation reduction and redox are the largest category. Most of the chemical reactions that we deal with do happen to fall into this category. So we do have to be more cognizant of what this is. And then we've got your double replacement type reactions that could be referred to as metathesis or precipitation. And they do kind of behave the same way as an acid base reaction. So that kind of functions in the capacity of a double replacement. So that's where there's kind of a little bit of overlap, and we need to be able to distinguish specifically not just a double replacement, but what is actually happening in the reaction. And that's where we have to kind of look closely at things like the states and what's going on. So as we go through, we're going to kind of just briefly hit on acid-base reactions, which anything that starts with an H in your formula. So we got things like HCl, HNO3, H2SO4, all of these HCN, all of them start with an H, and they are deemed as an acid when we mix an acid with a base. Now, some reactions can have an acid but no base, which means that they are not an acid-base reaction. They would fall into another category. So it's important that we are aware of that situation. So in this case, we're going to have an acid that's going to react with a base. And typically what we are focusing on is bases with a hydroxyl, our hydroxide group, an OH minus. And what ends up happening is we add the hydronium, which is the H plus part of the acid, and it mixes with the OH part of the base, and it forms HOH, which we know as water. And so this is where we get that neutralization concept from. We take the acid component and the base component, and we basically make them neutral by mixing them together so that we don't have to worry about those ions reacting or interacting. And so as a result of the H and the OH combining to form water, we're left usually with metals and nonmetals, which they will form an ionic compound, which we refer to as salt. Now, a lot of books, a lot of textbooks, and a lot of courses introduce this as like HCl plus NaOH equals salt and or NaCl and water. And so we need to not get confused with the word salt. Salt simply means an ionic compound. So make sure that we understand that an ionic compound is a metal and a nonmetal. Now, redox reactions, like I said, are where we have oxidation and reduction. So there's a two-part fold here, and these are the ones that are probably the most complicated. What actually happens in a reduction reaction, a reduction and an oxidation reaction, is somebody is losing electrons, and another person or another party in the reaction is going to gain those electrons. And so we have to really pay attention to the charges and how we identify the charges on per element. And so there are subcategories, or these are ones that are not just redox, but we can classify redox as oxidation reduction plus a single replacement. We can have combustion, we can have synthesis, and we can have decomposition. So if you think about a single replacement, somebody has to be single, and they're going to replace somebody that's not single. And then we've got your combustion reactions, which there is also one called synthesis combustion, which we'll talk about that as well in the upcoming slides. And then we have synthesis, which is building up. So if you think about, we're going to synthesize something, we're going to build it, we're going to make it bigger. So typically what we're looking at here is a building up process in our reactions. And decomposition is just like we think about when we decompose something, we break it apart, break it down. And so this is where we're going to be breaking our reactants into more products. The overall theme that we see with redox reactions is the oxidation number changes. If you recall, oxidation number refers to the charge. So what we're seeing here is that these electrons are going to exchange. Somebody's going to lose, somebody's going to gain. And the process of that, we identify the different components that make up the oxidation reduction component, and they go hand in hand. You can't have one without the other. Kind of like, I think there's a song out there like we go together like peas and carrots, like things that you find together, like mashed potatoes and gravy. You're going to find them together. This is what you're going to see for redox reactions. And we're going to be having to attract these electrons because they're the ones that are exchanging and causing this to take place. Now, precipitation reactions do not involve changing the charges, and that's one of the biggest things that's different here. What we're going to be looking at is a double replacement, which means two ions are going to swap places. And as a result, we don't necessarily change the charge, but we change who they're bonded to, which can ultimately change the formula. So again, this goes back to formula naming and writing is very important, because if you don't know how to write the formula correctly, we're going to have a problem. Now, one of the products is typically in a precipitation reaction. If we think about precipitation, we usually think about rain, snow, sleet, things like that. Especially here in Texas, we don't think about snow a whole lot, but God forbid it's going to come out of the sky. We're going to have a problem, and the whole city is going to shut down. But when we start looking at precipitation, just like the rain and precipitation falls from the sky, what we're going to be looking at is the fact that in a precipitation reaction, it forms a precipitant where basically a solid is going to come out or pull out of the solution and fall to the bottom. That's where we kind of can get the similarity between precipitation reactions and precipitation, because the solid falls out and we are left with the liquid in the solution, and then we have a solid component. But we typically start with two aqueous solutions to begin with. So we're going to be talking about combustion, synthesis, combustion, decomposition, single replacement, and double replacement, so that we can kind of predict how these reactions will go, and we can kind of figure out what's going on with the products. Again, some of this will require doing the work on the board, so I want to just kind of focus or mention that this is what we will be doing in order to get this process going for you to understand. So, combustion reaction is typically the sequence where we take a metal, typically plus oxygen, and we combine them with a lot of heat, or we heat the sample up to its temperature point that we need. And what we end up getting is a combined, what is known as a metal oxide. So we combine the metal with the oxygen. So what we have to understand here is that we have these elemental forms, which, remember, O2 is part of those diatomic molecules, which means when they're bonded, they have a charge of 0. Looking at the metal by itself, whenever it's not bonded, it hasn't lost electrons, it hasn't gained electrons. And so when we actually combine it, we're going to be losing and gaining in order to get a charge so that we can create that metal oxide or a ionic bond in the process of synthesis combustion. But what really makes this a combustion per se is the fact that we have this O2 as a reactant. So usually when we see O2 on the reactant side, we have some kind of combustion happening. So that is important to know. Now, when we start looking at a true combustion, this is kind of like gasoline powered engines. What we're looking at is the fact that we're going to have a hydrocarbon, hydro referring to hydrogen, carbon referring to the fact that we have carbon with it. Sometimes you'll occasionally see like a CHO combination, and those are known as hydrocarbons. And what we're going to see there is the fact that we have carbon and hydrogen. It combines with oxygen. And in the process of combining with oxygen, it produces always carbon dioxide and water. So you have to be able to identify the fact that we've got carbon and oxygen, and then they bond and exchange these electrons, and we create carbon dioxide and water as a byproduct. So that's something that you are going to have to kind of just commit to memory, is that CH or any kind of combination of CH, CHO plus oxygen in the form of O2 will produce carbon dioxide and water. So how do we know, or what do we look for? In the fact that we have a combustion reaction, we're going to have the product is going to contain something combined with oxygen. If you notice, the carbon combines with oxygen, the hydrogen combines with oxygen. So the hydrocarbon is then split and we combine it with oxygen. So products will contain this oxygen component in a combustion reaction. So what we're going to look at first is a synthesis combustion or a metal oxide that is being formed. So it is important that we note here that we do have this Na S or a solid sodium, and then we have this gaseous oxygen. And what we do is we heat them up. Now, what we have to do is we have to understand that Na initially has a charge of 0. Why? Because it's in its elemental form. The only time something takes a charge is when it has formed an ion, when we're talking about something in the metal, non-metal category. And so something had to have lost or gained electrons. But when we're talking about single substances by themselves, they do not have a charge. And that's something you should write in your notes and put a star by it, and asterisk single elements, or even things like your diatomics, they are going to be a charge of 0. And that's really important in the upcoming in the upcoming topics that we're just going to talk about now. So what we're going to do is we're going to take a look at the board, and we are going to form this reaction. So let's see if we can swap this out. So we've got Na2O. So in this particular case, we're going to have your Na solid plus your O2 gas. And we're going to figure out what's going on here. So elementally, what we are looking at better. I think that shows up better for you guys. We're going to look at the fact that we've got plain solid sodium. Now, what I have here is a card that basically there's nothing that has happened to it. And what we're going to be basically saying is we're going to be bonding it with 2 oxygens over here. Now, if you go on the periodic table and you look at the periodic table, you're going to find that sodium, when it bonds, or the most common charge of the ion that we have, let's put it down here to start. Na has a 1+ charge. So we know that Na is going to have this 1+ charge. And we know that oxygen typically, when it likes to form a bond, is it likes to be a -2. So we know that this is what oxygen by itself will form. So what we have here is we have Na with a +1 and O with a -2. Now, if we were to look at that, we can clearly see that this right here is not a equally bonded structure. So now we have to figure out what the new structure is going to be in order to make them equal. And so what we're going to do here is we're going to kind of put our puzzle pieces together, and we're going to find out that we need another sodium in order to balance our equation. So when we balance our structure, that means that we need 2 of the NAs to 1 oxygen. And so we're able to write the product now as Na2O, and we know that that is going to be our product. Now, we still have to go through and we still have to balance our equation. And so at this point, the first thing you might want to say is, oh, well, I have 2 NAs and so I need to have 2 here, which that could be a start, but we still have to balance the oxygen. And in this case, we've got 1 oxygen. Over here, we've got 2 oxygens. And so we know for a fact we're going to have to put at least a 2 here in order to get those oxygens balanced. And so now my oxygen is 2. My oxygen is 2 times 1, which is 2. But that also means I now have 4 Na. So what we're going to look at now is we're going to kind of look and see what's going on with our equation. So in this case, if I wanted to continue building this, that means I actually am going to have a total of 4 blocks in order to balance this one. My O2 is still 1 O2, but you have that kind of like that middle part, we've got 2 atoms there. And then over here, we're going to actually need a second set of blocks, which is going to be your Na. And we're going to come down here and do our pieces. So this is going to be our oxygen with our 2 minus and our Na with a 1 plus. So now our equation is balanced. Now what we have to do is we have to take it one step further when we deal with oxidation reduction reactions, okay? And those require us to discuss the fact that we are going to be dealing with, I just flipped the screen, so hopefully now it will show the correct direction for you on the screen. So what we're going to look at here is we're going to see that we've got 4 NAs, 2 oxygens. We have 4 NAs and 2 oxygens on our product. So we are balanced. But what we have to do is we have to write something called a half reaction. And when we start looking at a half reaction, what we're going to do is we're going to look at one substance, and then we're going to look and see what happens with the other substance. So the first thing we're going to look at is we're just going to kind of look at this Na that we have here. All right, so what we're going to do here is we're going to say that I have 4 Na. Okay, so we have 4 Na. And what we're going to look at is that they have a charge of 0. Why? Because they're not bonded. They don't have any interactions. A charge of 0. Coming over here, our NAs are now with a +1. So what happened to them is we went over here, we got 4 NAs with a +1. So what we're doing is we are identifying the fact that we've got 4 and we went to 4 that lost an electron. So we still have to represent this half reaction and we have to balance this reaction. So what we're going to do is we're going to kind of bring in some more visuals. And what we're going to talk about is these visuals represent the electrons that we lost. So here is the filling in piece from what we had. So we had 4 of these. We can go ahead and bring in 2 more. So now we've got our 4. And so we are going to go ahead and fill them in. These are the electrons that we lost. So what we have to do is we have to write an expression that illustrates the fact that all of them now look the same. They're all going to be 4 blocks that all look the same. If you notice, we now have 4 solid blocks when we have those extra electrons put in there for the ones that they lost. But we can't put them together anymore because we said that they lost the electrons. So what we're going to do at this point is we're going to backtrack and we're going to pull them out. And we're going to label these electrons. So these are short is E with a minus sign. And so what we're going to say here is we have 4 Na at a 0 charge goes to 4 1 plus, because we have 4 with a +1, plus we're going to have 4, 1, 2, 3, 4 electrons. So when we write this half reaction, what we're basically saying is that we have to balance it by saying which side those electrons go on. So this is what's happening for the 4 Na. All right, so now we've kind of dealt with Na, so we're going to get rid of those cards so that we don't get those confused. And what we're going to do is now we're going to talk about these oxygens. So we formed an oxygen. We had 2 of them that were at a 0 charge. And now we're going to end up having 2 of them with a 2 minus. Okay, so we had 2 atoms. Each one of them lost electrons. So now we end up having 2 with a 2 minus. So we're going to write what this expression looks like. We're going to look at it and we're going to say O2 goes to 2O with a 2 minus. Again, it's still balanced. We have 2 oxygen and we have 2 oxygen. So what we're seeing here is that they are balanced. So now we got to figure out where do the electrons go within this equation. Well, if I wanted to put these 2 pieces together, we would definitely see that there's a deficit. Well, what is the difference between this 2 minus and this block? The difference is the oxygen gains 2 electrons. So you can put the 2 electrons there and we can see that, or you can put them on this side if it makes you feel better. You can put them over here and you can see that these structures now replicate each other, but they weren't attached in the beginning. We had a charge of 0 because it was non-bonded. So what we're saying here is, in order for me to make this side equal, I'm going to have to add 4 electrons, 2 for this one, 2 for that one. 2 plus 2 is 4. So I'm going to get 4 electrons. And so when I do that, I'm going to be able to create my 2 oxygens with a -2 charge. So what we've done is written 2 half reactions. And if we put them together, we'll be able to see that 4 electrons were removed from sodium so that those 4 electrons could be added to the oxygen to form 2 O2 minus. And now that they can go together because the positive will attract to the negative to form that new structure, sodium oxide. But it does matter when you start looking at balancing an equation, because if I didn't balance the equation, I would say 1 electron goes to the 1 electron over there. And I would need to understand that there's 4 so that I can account for the 1, 2, 3, 4 that I have on the oxygen for the O2s. So it is really important that we understand that. So now that we have had this expression, we need to understand and apply the next terms that we start to see. So there's something known as oil rig, or you may have learned it as Leo says GER. Okay, so I don't know which way you've learned it in the past. Maybe you haven't learned it at all. But if you haven't been exposed to it, it's fine. What we're going to look at here is that we have oil rig, which oil stands for oxidation is losing. What are we losing? We're losing electrons. So we have to look for the equation that is kicking some electrons out from the beginning to the end. Now, Reg stands for reduction is gaining. And so when we start looking at that, that means that I have to say, initially I didn't have electrons. Now when I'm finished, I do have electrons. So what you see here is you've got your oil rig. So oxidation is losing, reduction is gaining. So it's important that we have that. Now Leo says GER is very similar, but it's just another, or Leo the lion says GER, you may have heard it that way. Losing electrons is oxidation, gaining electrons is reduction. And so what you're seeing there is that acronym is telling you when I lose electrons, just like oxidation is losing, we are going to be called oxidation. When we have reduction is gaining, okay, or gaining electrons is reduction, what we're looking for is who didn't have them and who gained those electrons. So in this particular case, we've got oxygen who gained the electrons because we went from having no extra electrons to having extra electrons. And for sodium, we went to not having any to kicking them out, where we lost those, or we had those cards, if you remember, the cards where we've lost those spaces, we lost electrons. So this is known as the oxidation reaction. This one is known as the reduction reaction. And they partner. Somebody has to lose and somebody has to gain. So in this case, oxidation is losing, reduction picked them up to gain them. And so we do have that partnering pair. Now, the last part of the vocabulary that you need to look at would be known as your oxidizing agent and reducing agent. So if you think about like a insurance agent, or if you think about like a professional like ball players, or people that, you know, they're movie stars or they're into like films and stuff, they usually will hire an agent. And that agent basically goes and seeks work for them based on whatever they're needing. So in our particular case here, the sodium said, I need to lose electrons to become stable. So I need you to go find somebody who's willing to take on electrons. So the agent says, that's fine. You want to undergo oxidation, so I'm going to go seek somebody who wants to be reduced. So this is known, the beginning part is known as a reducing agent. Why? Because he's looking for reduction Because in order for me to undergo and give away these electrons to become stable, I need to find somebody who's willing to gain those electrons. So this is known as the reducing agent. And the other substance would be the one known as the oxidizing agent. I want to undergo reduction, meaning I need to collect electrons. And so I need you to go find somebody who's willing to produce those electrons. And so this is known as the agent that's looking for oxidation, or looking for somebody like sodium that's going to be willing to give me up. So these would be known as your oxidizing agent. So oxidizing agent, reducing agent, they're actually opposite from what the reaction would be. And then oxidation, we identify it because they're the ones that kick out the electrons. And then reductions are the ones that are going to gain those electrons, and you're going to see them. Another way that you can look at it is in this reaction, the electrons end up being, when it balances, it ends up being on the product side. Whereas on the reduction reactions, they are ending up on the reactant side. So that's another way to look at it. Another question that you could be asked about these particular questions, as far as redox reactions, you could be asked how many electrons are involved. Well, these 4 electrons are the ones that were kicked out. They were also the same 4 electrons that were picked up in order to stabilize oxygen. So we have a total of 4 electrons in this particular reaction that we were used in order to stabilize it. So it does depend on us balancing that initial reaction. And if we don't balance that initial reaction, we can have some trouble. All right, so let's look at another example. So now, this one, I'm not going to go through all of the redox component on this particular one, just because it's super complicated and this is still a little bit new to you. So we want to pick up a little bit easier one in a second. But this is known as your combustion synthesis. I'm sorry, this is your true combustion, where we just did the combustion synthesis. This is your true combustion. This is where you're taking a carbon and a hydrogen that are bonded together, and you are going to then interact them with oxygen. So you're going to form that carbon dioxide and that water. Again, carbon reacting with oxygen, hydrogen reacting with oxygen, and we form that carbon dioxide and water. And obviously, you would want to go back through and balance this chemical equation as well. So now we're going to talk about synthesis in a little bit more detail. And that synthesis is what we're looking at, is where you're going to be having the combination of 2 or more substances, and they basically bond or they integrate with each other in order to form the charges that you would need. Now, this could be a molecular compound as well, not just strictly an ionic. The ones that you're going to be assessed with probably in this course, if you're asked to predict the product, is going to be a more of an ionic structure, where you're going to take 2 of your metal, and you're going to take a metal and a non-metal, figure out what their most common ion charge is, and then bond them together respectively. So this is what's going to be happening. But again, this goes under your synthesis combustion, which ultimately comes back to somebody losing electrons, somebody gaining those electrons. So just kind of talking about what is a synthesis or a combination, a synthesis combustion reaction. You may have seen Garfield on some of the cartoons, and we all know that Garfield and lasagna, if they are in the same room, do not remain apart at all. We understand that was his favorite dish. So synthesis reactions is just telling us that we're putting them together, and we're putting them together in a way that makes sense. And as far as Garfield is concerned, it's going to be in his tummy is where it makes sense. Okay. So here's an example of, again, another synthesis type reaction, where what we are doing is we're going to take the elemental form of hydrogen, the elemental form of chlorine, and then we're going to be producing HCl. So let's take a minute and let's kind of look at that and break that down based on the reactions that we see here. So we're going to have we're going to have H2 plus Cl2 is going to give us HCl. All right. So here's our equation. We're going to know that the elemental form of hydrogen gives us a 0. We know the elemental form of chlorine is Cl2, so that's also a 0. When it is bonded, we should know that hydrogen is a +1. And we should also know that chlorine, when it forms a bond, is a -1. So what we're going to look at here is we're going to look at our half reactions that we start to form. So we're going to say H2, 0. And let's go ahead and put that balancing in there just so that we're all good. So H2, 0 is going to be going to 2H with a +1. So if we need to look at it, we can look at our 2H plus, and over here, we're going to have our 2H molecules together. And so what we're looking at here is that we do have an H2 going to an H plus, and if you notice, we're missing that inside. So in order to balance these out, we're going to have to go plus 2 electrons because we had to have 2 little dots fill in those spaces that are empty. So what we see here is that I don't have anything missing over here. I have 2 electrons missing, which means oxidation is losing. So this would be represented as my oxidation reaction. By default, that means that H2 has to be my reducing agent. Now, let's look at the next half reaction. So in this case, we're going to have Cl2, and that's a charge of 0. Again, elemental forms are a charge of 0. And we are going to take it to 2Cl with a 1 minus. All right, so now what we're going to do is we're going to take our Cl. We have our 2 Cls. Both of them have not lost any electrons. And we are going to then produce 2 chlorines with a 1 minus, which means they have gained electrons. So from start to finish, in order to make this equal, I've got to add some electrons in here to make them look the same. When I do that, they now look the same, which means I am a balanced reaction. So which side gets the electrons? We're going to go 2 electrons plus my Cl2 gives me 2Cl with a -1. So I'm going to have to go ahead and put those 2 electrons here. Again, the electrons for an oxidation are found in the product side. For a reduction reaction, they're going to be found in the reactant side. And so again, by default, since this is the reduction equation, that means that this has to be the oxidizing agent. So by default, they're going to be seeking oxidation because we want to undergo reduction. So hopefully this is helping you understand how to go about doing your oxidation reductions, your reducing agents, you're understanding the electrons and the exchange that electrons do have. So let's see if we can talk about the next equation. All righty, so now when we start talking about synthesis, we're going to kind of put these together and we're going to think about their charges that we start to see. So again, what we're going to look at is our equation, which is going to be an aluminum molecule plus chlorine. So we got to figure out what is going to happen here. So we're going to stop the share. So you can see the board here. So we've got the aluminum, and then we're going to have chlorine. All right, so chlorine here, we know that when it likes to form its most stable ion, typically it's going to form a -1. There's my -1 that is going to form. All right, now we know that aluminum is part of group 13 or 3A. And so we know that when it forms a bond, it wants to form it as an Al3 plus 3. So in order for me to satisfy this structure, I know I'm going to need at least 3 chlorines in order to satisfy my 1 aluminum molecule. So that means we're going to have Al, one of those, and we're going to have Cl3. So now we do have to go about balancing our equation, which means 2 and 3, the lowest common number is 6. Once you have that 6, you're going to go ahead and put 2 in front, which means you're going to put a 3 here, and we'd have to have a 2 in front of aluminum. Again, if you're struggling with balancing, practice balancing is going to definitely help you as you go through with these and identifying how many electrons and all that good stuff. So we have your aluminum, we have your chlorine, and we have our aluminum chloride. So let's take a minute and let's kind of break down what we have beforehand. So you do have 2 aluminum molecules, which are going to produce aluminum with a +3. So let's set that up a little for it. So we balance. And don't have enough parts for this, so we're going to do Cl2, Cl2, and then all Cl2. So we've got our molecules that we have set up so that we can balance the equation appropriately. So aluminum, this is what it's going to look like initially. When it goes to the other side of the equation, it's going to look like this. So what happened to my aluminum? It went from here to having some holes in it. So we have to ask ourselves what happened. Well, and what we're going to see here is that it lost 1, 2, 3 for the first one, 4, 5, 6. So we lost a total of 6 electrons. So we would need +6 electrons in order to fill in these holes so that we could come back and look like the original one. So in this case, we understand that our half reaction would look something like 2Al goes to 2Al through the plus, and then we're going to say +6 electrons because we needed 1, 2, 3, 4, 5, 6 to satisfy the balanced equation. All right, so now let's look at the chlorine. So this one went to 2, this one went to 2, this one went to 2. So now what we're looking at is the fact that I didn't have any electrons, and now I have extra electrons, which means in order for me to move forward, I've got to put these electrons that we lost from this aluminum, they're going to have to go and they're going to have to create these spaces so that they can now be balanced and they can look like the Cl minus. So in order for them to turn into that, we had to add, we have to go 6 electrons plus our aluminum, plus our chlorides, 3 chlorides give us the 6 Cl minus. So that to write that half reaction or what that reaction would look like would be that we're going to have 3 Cl2 with the charge of 0, and that's going to go to 6 Cl1 minus. But we're going to have to go ahead and put those 6 electrons here in order to balance it out. So what do we have? 0 going to a +3, kicking the electrons out. This is my oxidation reaction. 6 are being added, so this is reduction is gaining. And so since this is the oxidation, this is called the reducing agent, and this one will be called the oxidizing agent. So hopefully that is helpful with understanding what we have for those structures. All right, so now let's look at a decomposition reaction. And hopefully we can kind of have the idea down so that we can walk through some of these a little bit easier. Now, decomposition is when we're breaking things up. So Fred and Wilma from the Flintstones, they were dancing together and then they decided that they didn't want to dance anymore. She was just tired of her feet getting stepped on by Fred. And so they decided to go their separate ways and not dance on the floor. So they are taking what was together and they're splitting up for just a little bit. So here we're seeing that happen with water, where we take water, we put it under electrolysis, a process known as electrolysis, and therefore what we start to see is that it is breaking down into their respective ions. So when we're looking at our structures, sometimes it's hard to see for binary or I'm sorry, for multiple things, like typically like your molecular compounds, but we're going to focus more on your ionic structures at this particular point. So we know that potassium, it's bonded. So because it's bonded, we know that it's going to have a charge. If we look at the periodic table, we find that potassium has a +1 charge, which essentially means that they're found in group 1. They have one valence electron. They become satisfied when they have a +1 charge. So we know that here we have a +1. Bromine is found in the halogens, which is group 17, which means that that's going to form a -1. It has 7 valence and wants to gain 1 more to be stable. Now, they're going to go to their elemental forms. And this is where not knowing your diatomic molecules can kind of mess with your results, okay? So we do know that bromine is part of that H7 acronym. Again, diatomics, we have H7, which is hydrogen, then we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So there's your 7. They are always going to be 2, and they're going to have a charge of 0. That's their elemental form. So we're going to take potassium, who is singular by itself, and we're going to say K, and that's going to be solid because most metals are solid at room temperature. And then we're going to also have Br, which is going to be Br2, because elemental form is going to be your diatomic structure. So what we're going to do is we are going to break this particular structure into its respective components. So we're going to look at K has a 1+ charge, and it's going to be going to K solid with a 0 charge. So now this is actually reverse of what we've been doing. Okay, so, and that's okay. That's absolutely okay that it's reversed, but we still have to balance the equation. So in my reactant side, I have the +1. So what I'm going to realize is that on the beginning, I'm missing an electron. So in order for me to balance that in the beginning, I'm going to have to actually go ahead and add electrons to it so that it can satisfy this side and make it whole, because it's saying that the potassium is charged 0, which means it's whole. So at this point, I'm going to have K plus electron for every number of K that I need when it's balanced. And therefore, I'm going to have to add that extra electron, at least one, while we have it here. But let's go ahead and make sure that we do have the right numbers so that when we're balancing it, it'll be balanced for good. So we have Br2, we have 1 Br, which means I need to put a 2 here, which ultimately means I need 2K. So instead of 1 electron, I have to change all of this to 2 in order to have a balanced equation. So now let's look at bromine. Initially, I have 2, and they're Br with a 1-. And in the end, it goes to Br2 with a charge of 0. So what you're seeing here is the fact that I am going to need my extra electrons here in order to make that bromine look like that Br with a 1-. So again, this is different than what we were doing. We were typically seeing the ones taking the electrons and everything. So this is actually kind of like reverse. Okay, so decomposition is the opposite of synthesis. So what we're seeing here is that we're gaining electrons. So gaining electrons is reduction, or reduction is gaining, whichever acronym you want to use. So this is my redox component. And then this means I have my oxidation, and oxidation is losing. And we're seeing that we had a 1 minus and now we're going to a 0, and we kick these electrons out. So what we're seeing here is that this is the oxidation. So if we go back to the reactant side, the reduced becomes the oxidizing agent. The oxidizing one becomes the reducing agent. So hopefully this is making a little bit more sense as we're going through. And we do have a total of 2 electrons involved in this exchange in order to make it happen. Now, let's go ahead and look at single replacements. I've coined these reactions the home wrecker reactions. Now, most of us are very familiar with a home wreck situation where somebody is distracting the person that's in a relationship and they decide that they want to be in a relationship with them. And so, as a result, what you end up seeing is that the original relationship is broken up and they find the person with the other partner. Now, what you're looking at here is that we have a couple and we have somebody who's single, hence the word single replacement. So what we have to do is we do have to do a test to see if this is even going to happen, because we do know that there are relationships, regardless of outside forces, that choose to stay together and they're not affected by advances of other people. And so what we're looking at is we have to determine how strong this person is. If this person is stronger, nothing happens. If they're not, and this person is stronger, the single person is stronger, then the reaction will take place. And what will actually end up happening is A will come in and kick B out. B will now be the single person, and A will be the one that carries on with the relationship. So you have to look at the relationship that we're dealing with as far as who was single, who was double. And this is kind of an example of Fred and Wilma, and then Betty comes in and is like, Fred, I'll dance. I want to dance. You want to dance? Cool. Let's go dance together. And Wilma sits on the sidelines. All right. Now, when we start looking at a single replacement reaction, what does that look like? Typically, for the ones that we're going to be focusing on, there's going to be a solid metal. We have a metal, non-metal ionic compound that is aqueous. And what ends up happening is these have the ability to give their electrons over so that silver can now come out, be whole, and copper can come in and form the relationship, giving silver the ability to be solid. So what we're seeing here is the exchange of the electrons allows a metal to seem like it disappears and a new metal to seem like it miraculously forms, but it's coming from the solution itself. So this is how you can kind of know who is stronger. If I am higher on the list, I am stronger than anything below it. So if we were to pick calcium, calcium is stronger than every single one of these. So if calcium is single and coming across anybody that is in a relationship below it, that means calcium is kicking them out. Calcium is going to get that relationship. Now, however, calcium cannot be barium, potassium, or lithium. So if they are in a relationship with one of those three, guess what? Nothing is going to happen because those molecules are more aggressive than calcium because they're above it. So it is important that we can look at that. So keep this in mind. We'll come back and look at it in a second, but we're going to go ahead and we're going to see, first off, does the reaction occur? If it does, then we got to figure it out. So here's a shortened version. It doesn't have everything with it, but I do want to point out real quick before I move on. You can see here that aluminum, its oxidation state in this position is a +3. Zinc, its position is a +2. I'm sorry, a +2. Chromium is a +3. So only when we're dealing with these particular states, because there are others that may fall in a different order. Like you could have an iron with a +3 versus an iron with a +2. So if you want to know what charge they would be forming, you can look at this chart. So we have copper. So in this particular case, we're dealing with copper with a 2+. So that's where that copper would be. So we have iron and we have copper. So we need to see who was more aggressive, copper or iron. So if we look at this chart here, we're going to see that we have copper all the way down here, and we have iron. If we look at our table, we have iron that is about halfway up. So iron, because it's higher up in the chart, is stronger than we see the copper. So that means copper is weak, iron is strong when it comes to bonding. So that means copper can't hold on to sulfate because iron is more aggressive and iron is going to, he says, I don't care what you do, copper, I am going to win sulfate. You don't have an option in this. And so iron is going to come in, copper is going to come out. And so what you're going to form on the other side is solid copper plus iron sulfate. Now, the reason we can go ahead and write FeSO4 is because we do know the charges, but you still have to balance charges. So you might want to put that down in your notes. You still have to balance charges. In this case, iron happens to be a +2, excuse me, and sulfate is a -2. So they are a 1-to-1 ratio, and we balance them appropriately or accordingly is what we have done. So what we're going to see here is that we now have several players that we have to focus on. And so let's take a minute and kind of go back to the board and see if we can kind of focus on this reaction a little bit more. Again, these are still all redox reactions. We haven't gotten past redox yet. So all of these, if you see them, are still considered to be redox reactions. So we are going to look at, we said, iron plus copper sulfate is going to form, we said it's going to kick out copper solid, and then we were going to form the iron, Fe+2 plus SO4, and that's going to be aqueous. So it is important that we also note that. This is a solid, and then we get the solid copper out. So you actually will, in these reactions, you can actually see that exchange where you're seeing this metal color form. So what we're going to do is we're going to kind of look at all three substances. And that's the thing about single replacements. If there's three things, we got to deal with all three. So we're going to look at iron first. Iron is not bonded. So what should the charge be if iron is not bonded? The correct answer is all elemental structures have a charge of 0. Elemental is assuming also, or is also including your diatomic molecules. So in this case, iron has a charge of 0. Over here, iron is now bonded, which means we're going to go to iron. And we know that it's a +2 because we could go back to that activity series chart, the one that has the rankings, and it was going to tell us that it's a +2 charge. So we know that it goes from 0 to a +2. All right. So we do know that it goes from a charge of 0 to a +2. Now, let's look at copper. Copper is in a relationship, it's bonded to sulfate, which means it's going to be a +2. And it goes to copper by itself, not bonded, elemental form. So think about it. What is the charge? It should be 0. So we're going to go copper with a charge of 0, and that's solid. Now these are aqueous because they're being sustained by the solution, and we do see aqueous here as well. So now we've got iron and we've got copper. So the last one is sulfate. Sulfate is bonded here, so it's a 2- and it's aqueous. And then we're going to see on the other side, we still have sulfate, 2- aqueous. Why it's still bonded, it's still the same number, it did not change the charge. So the first thing I want you to notice is that this one doesn't have anything happen to it. So these are what we know as spectator ions. And spectator ions are basically just like if you go to a football game, if you go to a soccer game or hockey or whatever sport you want to go to, you sitting in the stand are called spectators. Do you actually go out on the field and play? Probably not. You cause the team a lot of problems if you choose to do that. And so spectator ions are just kind of there to say, hey, you all can play. We're paying attention to you, but we're not actually involved in the reaction. We're just rooting you on and we're there to observe you and make you play better because you got people playing. I don't know if you remember seeing during COVID, one of the things that they brought in was that like the teams were still being tested and still playing and all this kind of stuff. But they weren't playing as well because there were no fans in the stand. So then they started selling digital tickets or whatever so that people could log in and it'd be like they have fans in the stand so that they would play better. And so we have to have the spectators to make sure that everything plays well and does what it's supposed to. So what we're going to look at here is the fact that we do see that sulfate stays the same. And so this is known as a spectator ion. So sometimes we can have more than one spectator and it's okay, but it's still the same concept. It's the things that don't change between reactant side and product. They look the same. So we basically can say that they are not really part of the story. Okay. Now, when we start looking at iron, it goes to an iron with a +2. So what had to happen? Well, if you go back to your cards, you think about your cards, we have a +2. And before, we had a plain iron at 0. So if you look at those, we have the missing electrons. So in order to balance it, we'd have to add 2 electrons. So if we wanted to write this so that we could see the reaction, we'd have to add 2 electrons to this side. So now we're going to look at the copper. The copper is the reverse. It's a +2 going to a 0. So in order for these to be balanced, I have to add the electrons to this copper on this side. So I want to add 2 electrons. So now, I'm seeing something is getting kicked out. Something is being added. So what we're saying is oxidation is losing. That's what happened. It lost 2 electrons. Reduction is gaining. We add those 2 electrons back. And then we know that for the oxidized species, we're going to seek reduction. So this is known as the reducing agent. And then our copper here would be known as the oxidizing agent. So we still see reducing agent, oxidizing agent, oxidation reaction where it kicks out electrons, reduction where it adds electrons in. And involved in this reaction is a total of 2 electrons. So iron says here's 2 electrons, so you can go be solid. And copper says, thanks, I'm taking those 2 electrons, and you can have the remainders of those. So hopefully that is explaining single replacement reactions. So let's take a minute and let's go back to talking about whether or not we can predict if they're going to happen. So again, you can still do oxidation reduction in these because that's what they are. They're still a broader category. You still can be able to identify oxidation, oxidized species, reduced species. You can talk about oxidizing agent, reducing agent, and then you can talk about the electrons, but you also have the added component of spectator ions in single replacement reactions. And single replacement reactions only happen when the substances are higher up that are single on the spectrum. So it is important that we know that. All right, so let's look at magnesium and sodium chloride. So magnesium and chlorine would be the 2 that are competitors. So let's take a minute and kind of look at where are they on our chart. So if we look at our chart, we have magnesium. And then we have sodium, which happens to be just above magnesium. Now, one thing that's really important to notice is the closer the 2 are together, if you were to do this test in a lab, the closer they are together, the less reactive or the longer it's going to take for the reaction to take place. The further apart they are, the more aggressive the reaction is. And it's very easy to see that. You'll see that the reaction happens pretty readily. So in this particular case, sodium is above magnesium. Well, sodium is in the relationship, which means sodium is the winner because it's higher on the list. So that means there's nothing that's going to happen. I can put these 2 next to each other and nothing happens. Even though magnesium is as strong as it possibly can, it's not stronger than sodium. So that relationship will remain intact and nothing will happen as far as a chemical reaction. So now let's look at nickel and copper. So again, what we're going to do is we're going to look at our spectrum. So take a minute and kind of look and see where they're located. In our case, we've got nickel and then we've got copper, but copper is pretty low on the scale. So the question we have to ask ourselves is who is the single one and are they stronger? So nickel is my single one and nickel is higher. So therefore this reaction will take place. Again, I'll help you out. You can always go back to your notes and you can see that nickel forms a +2 in this particular case. So when we're bonding, that will help. Copper is also bonded with the sulfate, which is a +2. So what we're going to see here is that, yes, we do have a reaction. Nickel's going to come in here and say, copper, you get kicked out. So we're going to form copper solid. And then we're going to have the nickel sulfate. And again, nickel sulfate is going to be aqueous, and then the copper is going to be the solid. So typically that's what we're seeing. We have this metal swap out when we start to see these single replacement reactions. So if we were to look at this and we wanted to look at the actual equation, what we would see here is that nickel is by itself with a charge of 0, and it's going to go to nickel with a 2+ charge. And if we look at that, that means I'm going to have 2 electrons here. And then if I want to look at the copper, copper is going to be bonded with a 2+, and it's going to go to copper with a 0, which means I'm going to have to add those 2 electrons. So that means copper is my reduction and oxidation is my nickel. If I wanted to look at this, this would be known as the reducing agent, and the copper would be known as the oxidizing agent. And then we would have a total of 2 electrons involved in making this reaction occur. The other thing that we need to note is, again, sulfate in this particular case is our spectator. So that one does not change at all in the reaction. So what about calcium and sodium chloride? So if we look at our chart, we're going to see calcium, it is single. So we have calcium is marked on the chart. Then we've got sodium chloride. So we're looking for sodium. Calcium is stronger than sodium. They're still close together, which means it's going to take a minute for the reaction to occur. However, calcium is going to win out. So in this case, calcium is going to come in and tell sodium go on out. So we're going to have an A solid. Because it's single, it has a charge of 0. And then we're going to have Ca, which by default is a +2, bonded to chlorine, which is a 1-. So in order to balance this, we get CaCl2 aqueous. So now we have the equation. We predicted what we were going to do. We wrote using the charges that we see. And so now we're going to kind of break it down. We've got calcium solid, and that's going to go to calcium with a 2+. In order to balance this, I'm going to be looking at 2 electrons, which means this is oxidation, and I have the reducing agent. And then I'm going to have an A with a +1, and we have 2 of those, because in order to balance this, we have to have 2 of those. And so what we're looking at here is we're going to have 2Na is going to go to 2Na with a 0 charge. And so we're going to have to add the 2 electrons in order to fill in that Na with a 1+. And so we're going to then have that this is the reduction and Na is the oxidizing agent. So hopefully this is making sense. Again, it takes a couple different extra steps. And in this particular case, we have Cl with a 1-, and we have 2 of those. Those would be your spectator ions. Those are the ones that doesn't change from the beginning to the end of the reaction. All right, so double replacement is one of the last big categories that we're going to focus on, because once we understand double replacement, we can understand precipitation, and we can also understand acid-base reactions because they do the same thing. They do not change charges, so we don't have to worry about chasing electrons anymore. But what we do have to worry about is making sure that when our charges come together, they are balanced. So we still have to balance those charges like we've been doing. So what happens here is that you can either swap your B and your D, or you can swap the A and the C position. So either metals replace metals or non-metals replace non-metals, but you don't want to move both, or all you're doing is swapping locations. You're still going to have the same partners. Okay, so again, only move one, either B to D and D back to B, or you're going to do a swap with A and C. So A goes to C position and C goes to A position. So here's an example. We got Wilma and Barney. I'm sorry, Fred and Wilma and Barney and Betty. And then what ends up happening is they swap partners and everybody is happy. So lack of better terminology, if we're using today's vocabulary, these would be like your swingers, your ones that swap their partners out that you have, okay? Or wife swap or whatever. There's several shows, reality shows where they take a wife and they swap them for 7 weeks or 8 weeks, something like that. And they see if they can still function. And so what we see here is the difference here between double and single is that one, we don't see the changes in oxidation number, but we have two couples. So it's important that we understand that nobody's going to be starting out with zero charges because they're both couples. So couples are going to swap. Metals will replace metals and non-metal position replaces non-metal. So you're going to pick one or the other to move. The big thing too about a precipitation versus an acid base. If you swap them in an acid base, you produce a salt and water. If you swap them in a precipitation reaction, what's going to happen is we have to apply the solubility rules. And those solubility rules are the ones that are going to help you understand whether or not they're going to be a solid, or if they're insoluble, they're considered to be a solid. If they are aqueous, or they are soluble, they're going to be considered to be aqueous, meaning when they go into solution, they are ions. So it is important that we understand that. So double replacement reactions can be called precipitation. When it's acid-base reactions, instead of having a solid, we produce liquid water. So that is the important thing. So let's look at our solubility rules. I kind of basically group these into three different categories. All right. So the three different categories are, you got your players, you've got your mostly players, but they'll get married if they can find their celebrity crush. So we've got those that will only get married with a celebrity crush. And then you've got the ones that they wear their heart on their sleeve. They are looking for love no matter where it is. Their intention is to fall in love for the rest of their life. So what we're going to do is we're going to kind of look and see which fall into which categories. So what we find out is that group 1 ions, these are your lithium, your sodium, your potassium, your rubidium, your cesium, your group 1 atoms. When they are in an ion state, meaning they've lost one electron, and we can throw ammonium in there as well, they will always be soluble. I don't care who they're bonded to, there is no reason. So these are players because they never want to precipitate out. They never want to get off the dating apps. They never want to stop dating. They want to constantly play. They want to constantly date. They want to constantly be single. They like to mingle. They do not look for a long-term committed relationship. All right. So which ones are those? Those are your group 1s and your ammonias. Okay. Now, you also have your nitrates and your acetates and your perchlorates. Perchlorates are the ClO4 with a -1 charge. All of these are players, which means if I see them, they need to be a red flag to say, hey, we ain't getting anything that's going to precipitate with you. Okay. Nothing is going to fall out. You are going to continue to be single in the beginning and the end of the reaction. Okay. Typically, these become what are known as spectator ions. Okay. That's the important thing to kind of focus on. These often become the spectator ions. They are players. They don't want to be in a long-term relationship, and there's nothing you can do about it. They're not going to change their mind. Now, we have players that are going to be most of the time, but then we have those ones that are just like, if I could marry my celebrity crush, I get married tomorrow. Okay. But other than that, I want nothing to do with marriage. All right. I think I saw something the other day about Taylor Swift, and it's like they commented she made all these people not like men, and now all of a sudden she's getting married and wanting to start a family. For somebody who was single that she was, right? So she, if you want to look at it, she found her celebrity crush. That's not the case, but we can pretend that that's what the case is here. All right. So what we're looking at here is chlorine, bromine, and iodine pretty much will be soluble unless they happen to come in contact with silver, mercury, lead, and occasional copper. Okay, so what we're looking at here is that unless they're bonded to these people, guess what? They are going to be single and mingle. Okay, that means that they've got all these dating apps open, they've got all these profiles on there. They are looking to have a good time. They want nothing to do with a committed relationship. Sulfates are similar. They are pretty much, they like to be players unless they come across calcium, strontium, barium, silver, or lead. So it's really important that we understand who are ones that want to marry their celebrity crush, and only those celebrity crush, nothing else will make it happen. Otherwise, they fall into that. They want to be single, they want to be mingling. Now, we have our ones that are looking for true love. They will bond with anybody except the players. The players won't form a relationship with them. But if it's anybody else, they are pretty much down for trying to write a love story with them. Okay. And so when we start talking about precipitation reactions, we got to talk about these things like complete ionic and net ionic and molecular equations, which is essentially telling their love story of how they fall in love. So what we have to look at is unless they're bonded with these players, phosphates and carbonates are going to be solid when they are mixed. Okay. So they might start off as ions. They're going to be on the dating apps, but then they're going to find somebody that is not one of these and they are going to fall hard and fall out. The dating apps are gone. It is going to be nothing but the person that they are with. Now, when you look at hydroxides and sulfides, they're the same way, but there's a few more exceptions. Be like the sulfates. You got that calcium, strontium, barium. So for the most part, they will be insoluble. They will be a solid. But if you have them with their group one, ammonia, any of these other ones over here, um, I'm sorry, they're not going to be these. They're not going to be those because we have the negative charge. My bad. These are ones when you look at positive ions. When you look at these, if you're with the calcium, strontium, barium, or group one or ammonia, then they are going to be players or they're going to be with the players. So they're not forming a romantic relationship. However, when we look at carbonates and phosphates, they only care about group one. So they don't have the extra special um, conditions that would make them be soluble. So keep that in mind when you're going through. So these rules apply. So you have to figure out, swap their partners, rebond them appropriately with their charges, and then compare them to the rules to figure out is somebody soluble or is somebody insoluble. So looking here, we're going to look at lead nitrate and potassium iodide. So let's go ahead and flip back over to the board so that we can kind of work this out. Again, we're not changing charges on these. Okay, so what are we going to have? So we're going to have an O32. Make sure I got this equation right. NO32 NKI. All right, so we are looking at plus KI. So now what we're going to do is we are going to swap our partners. So let's take a minute and just kind of figure out what the charges are on everything so we can figure out how to swap them to rearrange them. All right, so we know lead is bonded to the nitrate, and we kind of can see that too. So remember back in formula naming, you can reverse crisscross. So we know we can come over here and bring this 2 up here. So that means we got PB with a 2 plus, and then we've got 2 NO3 with a 1 minus. So here's our lead, and then we've got our to NO3 minus. So this is what we've got going on here for the lead nitrate. Okay. Then we're going to come over here to our potassium. And we know that potassium, when it forms a bond, is a +1. And we know that iodine, when it forms a bond, is a -1. So this is what we have at the moment. This is my PB. This is my NO3. And this is my NO3. And then I have my K +1. And then I have my I1 minus. All right. So now I have what I need here. Okay. So now what I am going to do is I'm going to figure out how to swap my partners. Okay. So in this case, I'm now going to switch places. PB is going to come over here and K is going to come over here. Okay. So now K is a +1. K is a +1. And we're going to bond it with NO3, which happens to be a -1. So when I put them together, they're going to satisfy each other. So the first thing I want to form is KNO3. Okay, that's the first thing I want to figure out that I'm doing. Now the next one, I'm going to take my lead, which is a 2+. Okay, here's my lead. And I'm going to bond it with my iodine, which is a 1-. So I'm going to come over here and I'm going to have my lead and my iodine. And I want to place them here. And I want to see that it's got a deficit. I can't go and continue on writing this formula like this because I need a second one to satisfy the principles, but we have to have that 0 charge. So that means I have to add another iodine. So in order for me to write this formula with the balanced charges, I'm going to have to write plus PbI2. Okay, so this is where we're at. Now, this is where having your rules for solubility out are going to be really important. So initially, we can look at our formula PbNO3 here. We can look at this and we can be like, okay, we've got PbNO3 2, and we know that nitrates are part of the player group. So it doesn't matter who they're bonded to, they're going to still be players. They're still going to be on the apps. They're still going to be looking for a fun time, looking to date around. They are not looking to settle down. Lead, on the other hand, is like, hey, I want to settle down. I'm trying to find a family. That's what I want to do. I want to continue my life with somebody. Okay. So right now, when it's with nitrate, nitrate says, sorry, bud, I'm not your person. Okay. So this is going to be an aqueous solution. They are going to be soluble because nitrate says, I don't care who I am with, we're not getting in a long-term relationship. We're not precipitating out. Dating apps are going to stay on my phone. All right. So now we got K and I. K happens to be part of group 1. And since it's part of group 1, what it's basically saying is that I don't care who I'm bonded with either. Guess what? We are going to stay on the dating apps because we ain't settling down. This ain't us. Okay. So at that point, Ki is basically going to be insoluble. I'm sorry, it's going to be soluble. Okay. We're looking for something to be insoluble in a precipitation reaction. So now typically the starting materials are always going to be soluble. That's pretty much how we start out. Now, the question we have to ask ourselves is, do the products always end up being insoluble? If the products end up being insoluble. If they both end up being soluble, meaning nobody wants to get off the dating apps, everybody wants to be a player, then we typically have no reaction. All we did was put a whole bunch of ions together. They were singling and mingling and nothing happened. There was no romantic connection made to be long-term. Okay, so you do have to pay attention to that because they like to sometimes give those types of problems, especially on exams. So we're going to look at K. K again is a group 1. NO3 is also a group 1. Both of them are players. So we have to tell ourselves, since neither one of them want to form a relationship, they are going to be aqueous. Okay, they are not going to want to form a relationship. Now we're going to come over here to PB and I2. Iodine, for the most part, likes to be a player. However, if it can marry its celebrity crush, it says, I'm good to go. And lead happens to be one of those. Lead is a celebrity crush for iodine. So at this point, we're actually going to say that that is an insoluble substance. And so what that means is that it does not dissolve, it does not, it is going to precipitate out. So we're going to actually see a solid color of the, we're going to see a solid form out. And this is actually like a bright, like this color, yellow, school bus yellow, precipitate when we get this lead iodide to precipitate out. So what we see here is that KNO3 is going to end up being our spectator ions because nothing happened to them. They're still players, they're still ions in solution. But what happened is lead came in contact with iodine and they ended up forming PbI2, and that is their love story. So the next phase when we have a precipitation reaction is we have to write a molecular equation, and then we have to write a complete ionic, and then we have to write a net ionic equation. So that's what we're going to work on right now. Now, to start with a molecular equation, the first thing we have to do in a molecular equation is we have to make sure that we've said everything that we had, our states that we have, and then we have to make sure it's balanced. So in this case, I've got one lead. I have one lead. That looks good. I have two NO3, but I don't have two NO3 here. So I have to put two NO3. So if I put a 2 in front here, if I put a 2 in front here, I'm now going to have 2K and 2NO3, which is fine right now. But I only have 1K over here. So what do I have to do? I have to put a 2 in front there. And so now I got one lead, 2, because of the 2 on the outside, 2NO3, 2 times 1, which is 2NO3. I have 2K, 2K, 2I, and I have an I2. So that tells me I have 2 I's as well. So we are balanced with this equation. So what we're going to do now, this is my molecular equation. So this is known as the molecular equation. That's the molecular equation, all right? The next one that we're going to look at is known as the complete ionic equation. Complete means that I'm going to include all of the ions. Now, anything that's aqueous, I'm going to separate into the respective ions. So if you go back to kind of when we were looking at KNO3, when they are in solution, what actually happens is they break apart. Because what's happening in this particular reaction, what is happening is that when we have our PbNO3 and we have our KIs, and this is going to be balanced, we got our 2 KIs, and then we form our 2 KNO3s, and then we form our PbI2s, right? What happens is over here, once they get into that aqueous state, they no longer stay like this. What ends up happening is they split apart. All right. These also in an aqueous state split apart. So what that allows them to do is it allows them to literally be single and mingling and trying to figure out who they want to react with as they're going in the solution. And what happens is the negatives come up against each other. And it's like, oh, you either look like me or you're negative and I don't want to really bond with you. And they might come over here to the positives. Well, you are a potential, definitely a potential. All right. And then we have over here the +2. Oh, okay. Well, yeah, you're a potential, but if I don't want to be in a relationship, we're not going to settle down. So what we find out is that they can be single and they can mingle. But what ends up happening is the lead finds the iodine, and that's where we end up getting let's try to change these two. So the lead ends up finding the iodine, and that's where we end up finding that connection that we didn't have to begin with. So originally it was bonded here to the nitrate, and now they're finding the iodine. And so now they're happy and they are saying, hey, cool, I don't want to break up anymore. We're deleting the dating app. We're going to precipitate out, fall to the bottom. And what's left are the players in the solution above. And so this is when we can do a filtration and separate, get our solid out, and then we would have our ions in solution. And if you did the lab, in lab, you probably might have done something where you would like evaporate this out and reclaim a salt or something like that. And so what you're looking at here is that this is the story we're trying to tell. We're trying to tell what is precipitating out. And so by doing that, we end up getting our, we get our KIs and our leads initially. And then we swap the partners on them, and then we end up with the reverse. So this is what's happening in a double replacement reaction. And so what we're going to do is now we're going to write everything that was an ion to begin with. So if this was aqueous, we have to write our respective ions. So I'm going to have two of these, one of those. I'm going to have two of each of these. These are going to be ions because they're still aqueous, but this one is different because it now bonded and it's in a romantic relationship, and it says, I'm not getting out. This is my story. I'm getting married. This is what we're doing. So what we're going to say here to write a complete ionic equation is we're going to go PB, and we're going to write the charge because it's an ion. So we're going to write PB 2 plus, and it's in aqueous state, because if we don't say it's an aqueous, then we don't know that it's an ion that can be single and mingling at this point. Then we're going to write about this one. How many do we have? We have 2. So I have to put 2, and I'm going to have to put NO3s, and NO3 has a 1 minus charge. So I'm indicating that in my response. Here, again, I have 2 when it's balanced. So I'm going to say plus 2, and what is this ion? It's K plus. And again, these are aqueous. Sorry, I forgot to put aqueous over here. And then we're going to go plus, and this one's my I, and I have 2 of them, plus 2, I1 minus, and again, this is aqueous. So now what's happening on the other side of the equation? On the other side of the equation, I'm going to have 2K with a plus 1 aqueous. Plus I have 2 NO3 with a 1 minus aqueous. Again, they're aqueous, so they're still ions. And then I have my partners that aren't breaking up. So we're going to keep them together. Anytime you have a solid or a liquid, you do not break them apart. They remain together, and they are not separated in the process of writing a complete ionic equation. So we get PB I2, and that is a solid. So we went from the molecular equation here, where everything was together with just the states. We then looked and saw what was going on with the ions. And now what we're looking at is the complete ionic. We're writing everybody that was there at the party. Okay. Now what we're going to do is we're going to look and see who at the beginning was the same and who at the end is the same. And those are going to be our spectator ions. So PB was an aqueous in the beginning. In the end, PB is part of the solid. So I can't get rid of PB. PB now comes down to my net ionic. Net. If you think about a paycheck, if you were to say make $10 an hour, work 40 hours a week, your paycheck at the end of the week would be $400. But most of us know that even though they said you're going to make $400, our check is not $400 when we come home. Our check is much less because Uncle Sam decides to take his chunk out. And in our case, what we're taking out are the spectator ions. We're not going to leave them in the solution. We just want to know the love story of who fell in love. We don't care about everybody else. We want to know it first so we can figure out what actually happened. And then we're going to see that we just want to write their love story. Okay. So PB is different because we have our PB I2 over here. So we know that we're going to also have to bring that down. So our PBs are definitely different here. There, they're single. Here, they're in a relationship. All right. What about our NO3s? Well, I have two NO3 here, and look at that, I have two NO3 here. So that means they're the same on both. So that means that NO3, specifically two NO3, these are spectators. And you don't include spectators in the end story or in the love story. All right, so right now we've got our PB. Our NO3 we can cross out because it's the same on both sides. Our 2K plus, well, I have the 2K plus here, and I have the 2K plus here. So what I'm going to do is go ahead and cancel them out, add them to my spectator ions, and then we're going to go to 2I2. Well, I don't have two single I2s on the other side. My I2s are bonded in with my PBI2. So we're going to go ahead and bring those down. So we're going to keep those in our net ionic equation. So essentially, this is our love story. This is what happened. We have PB, okay, and that is going to be aqueous with a 2 plus charge, bonded with 2I with a 1 minus charge, and that's going to be aqueous. And we ended up finding out that we have PBI2 as a solid is who our couple is. So now we went from our molecular equation to our complete ionic equation to our net ionic equation. And this is the same thing when we deal with acids and bases as far as acid-base reactions. Again, we're going to have an acid and a base. They're going to swap partners. They're going to form H2O, which is going to be a liquid. So instead of having a solid, we're going to have H2O liquid. And when we do that, what we're going to end up having is the ability to see the same where the salts are going to be the spectator ions and the water. So we're going to have H plus OH equals H2O is pretty much always the net ionic equation for acid-base reactions, but they work the same way for double replacement reactions. So let's just kind of take a minute and look at this real quick and wrap up this concept of these equations. All right, so we looked at PB already. So what we're going to look at is NaNO3 going with Ki. So we know that we're going to go ahead and swap these partners out. So we know K is a +1. So we form K and then bonded to NO3. And it's a 1-to-1 ratio because K is a +1, NO3 is a -1, Na is a +1, and we know that I is a -1. So we understand that it's 1-to-1 to 1-to-1. All right, so we swap the partners, we get KNO3, and we get our NaI. Well, something is very obvious right now. We've got nitrate, which we know nitrates, it doesn't matter who they're bonded to, are always going to be molecules that do not want to form a relationship. So what we end up getting is KNO3 is going to be aqueous, meaning it is going to be soluble. It does not want to precipitate out. Then we also have sodium. Sodium and potassium are both group 1, which basically says we want to be single, we want to mingle, we don't want to precipitate out. All right. So with them, they refuse to get off the dating apps. They're going to forever date. And so at this point, neither one of these are going to form a precipitant. And these are the ones that are basically no reaction at all. And why is that? Because nobody forms an insoluble substance with them because they all like to precipitate. They all like to be single and mingle, and nobody wants to fall in love and get married. All right. So again, there's a lot of acronyms out there. There's a lot of tricks to remembering solubility rules. I encourage you that if you struggle with that, go find one of the acronyms, go find one of the songs, go find something out there to help you be able to quickly identify those so that when you're looking at your exam, you can identify them pretty easily and you're able to kind of move through and determine who is soluble, who's insoluble, so that you can write complete ionic and net ionic equations. So for now, that is all I have. Again, practice, 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 practice. I can't express it enough. The more you practice this, the better you'll get. It includes the balancing, it includes the new terminology, it includes knowing the charges to write the formulas. There's a lot of things that are needed in order to do this effectively, and it's not going to get better unless you practice, practice, practice. So until next time, you guys have a great rest of your day.